Okay, so we have this parametric function x equals t plus 2 and y equals 1/2 t cubed. And we said that we're writing a function input t. And now the output is not a single value but an ordered pair. Output a corresponding x and y. And x and y are each separate individual functions of t. So as an example, x is t plus 2 and y equals 1/2 t cubed. So can we now write that resulting curve for that parametric function, y is a function of x? So we can if we can get t in terms of x. If we can get t in terms of x and just substitute it in right there, then we got y equals a function of x. So you guys told me that t in terms of x is t equals x minus 2. So since that's t, we can just take that, put it in there. And then what does y equal? 1/2. Which is what we said. We said it's a cubic. What? Moved over to the right too. That's exactly what we're seeing here. Okay, so this one, can we write y as a function of x? What would you have to do? We'd have to first write t in terms of x, and then we can plug it in here. So let's get t in terms of x. What do you think? Good luck, right? Have fun. We got t cubed minus 3t squared plus 1, which would be difficult, if not impossible, with basic algebra to write t as in terms of x. T equals something of x's. But then we look at the graph, and what do we see? Is y a function of x here? No. This is a very odd curve. It's certainly not y is a function of x. If we were going to try to write y as a function of x, we might have to break it up into separate, like a y1, y2, maybe even y3, and write functions for separate pieces. Okay, but no. Okay, so we don't like this, right? So more complicated parametric functions, it's just not easy, convenient to write it y as a function of x. But this is very understandable, attainable, and so we just keep it expressed this way. Okay, so for a curve like this, that's based on two more complicated polynomials, we'll just leave this curve expressed as its parametric functions. Okay, but for easier ones, we can write y as a function of x. For instance, so here's one. Does it show up? Can you see the line? At least barely. Can you see it? Okay, so here's the parametric function, x equals 8t minus 3, and y equals minus 6t minus 2. So I want you to find y as a function of x. So it's a line, right? This line is not vertical, so certainly you could write y as a function of x, right? So go for it. See if you can do it. I'll start handing back the first stack. Right for day.
Okay, yeah, that's
Okay, start here.
equals 8 and minus 3 and t gives us 1 here and
Yeah.
put it in the bracket. So
Right, yeah.
x plus 3 divided by 8, right?
No.
I
I don't know if it's
X equals 8t minus 3. X plus 3. X plus 3,
Oh,
right?
you just saw it.
Yes. Divided by 8.
Oh, and then T. Okay.
Plug that in.
in.
And then from there on out, it's just algebra simplifying.
Oh, so that's actually probably fast.
It doesn't either.
Because I well, what's up? Well, I got the same stuff I did because I just put in like I just use like sample like that. So I put t equals 0 and t equals 1. So I have 2 points. So I got this slope from that. I know.
Okay, so you can check with what I did, see if you agree. So I found t in terms of x and just plugged it in and solved. It's not the only way to do it. But if you have something other than a line, this is going to be the way you want to do it. Agree with this? Are we good? Okay, so now when you're given y as a function of x, suppose I was given this, could you come up with, so now we're thinking we start with this, could we come up with a set of parametric equations, y as a function of t and g as a function of t, that produce the line? So how could we do that? So certainly looking at this right here, it seems like there's really no connection, right? Like, so to look at this and to come up with 8t minus 3 minus 6t minus 2 is like, you know, how would you do that? Okay, it doesn't seem like there's any very, you know, little connection, right, to coming up with these numbers. So forget that we did that, and let's say we started with this and we wanted to write x as a function of t and g as a function of t, and we wanted to do that easily. How could we easily do that? Again, we're not after this. This is not our goal, okay? Forget this ever existed. We just pretend we're starting with this and we want to write x as a function of t and y as another function of t that would generate this line. Real easy on yourself. Any ideas? Martin?
I think like if you can come up with the function for y, suppose you assume like we just have to replace x with t.
Yeah, what if we said x equals t? Then what would y be? Well, x equals t, right? So that would be negative 3/4 t. Would that do it? Yeah, that would do it. So now the question is, why? Because so t is always x. If t is always x, and then this would be x, well then that would be y equals negative 3/4 x minus 17/4. And that would be that line. So the question is, are these functions the same or different? Are they the same? Or are they different? Do they produce the same line? Do they produce the same line?
No.
No? They don't both produce this line right here? Well, we did the algebra using this, and we found this line. And then we said, well, this would just be the same as if x was t, and y was that. Right? So, are we okay that they both produce the same line? Just no?
I was just thinking like if you had like if your t equals 0, that'd give you different like, x values.
Okay, this is a different question. What I asked was, yes, my first question was, are they the same function?
Mm-hmm.
And then I asked, do they produce the same line? Okay? So, Martin.
I think we will produce the same line apart from when t is 0.
Apart from when t is 0. So when t is 0, what do we get here? We get an ordered pair. When t is 0, what ordered pair do we get? 0, negative 17/4. Okay? Right there. Okay? When t is 0, what do we get here? Negative 3, negative 2. We get this point. Do these parametric functions produce the same line? Yes. Are they the same function? No, they do it in a different way. They produce the same locus of points, but differently, right? So let me show you this. I can animate this. I think. So the blue one is the second one we did. All right? The red one is the one I gave you. So I'm showing you for different values of t. So I'm letting t change. So let's do this from 0 to 4. Still too much. Can you see the dots? So change this one more time. Do negative 2 to 2. Okay, now this will be good. So they're both producing the line, but in a different way for different values of t. Oh, there we go. For different values of t, it generates different points, but they'll both generate the whole line. Okay? So here's the blue one, and see, this is the current value of t right here. Down here is the current value of t. So this is an important distinction about parametric functions, is there could be many sets of parametric functions that could produce the same curve, but in a different way. For the same value of t, you'll get a different point on the curve in your variation of functions. So when we think of derivative, so suppose we come up here and we say, what is dx dt? So this is our red function, right? So dx dt is what? Is positive 8. And dy dt is what? Negative 6. And here, in our blue function, dx dt is? And dy dt is? So what is the meaning of dx dt? What is the meaning of dx dt?
Slope.
Is it slope? So is it slope of 8 and slope of 1? Is it slope? It doesn't make sense to think of it as slope, right?
Well, if you do a dy over dx,
But I'm asking about dx dt. You're right, dy dx is going to be slope. That's right. But I'm asking about dx dt.
How fast x is changing in respect to t.
So you said how fast x is changing with respect to t. Agree with that? All right, so in the red, as t changes a little bit, how much does x change? 8 times as much, right? So this is saying that for a change of t, your x is going to change 8 times as much. And in the blue one, for a change in t, x is going to change the same amount, 1 time, so the same amount. And so, do you see how that's reflected in the animation? Right? So for a change in t, you only get a 1 unit change in x in terms of producing points with blue. With the red one, for a change in t, well, you get 8 times the change in x for your change in t. And so that's why it goes the points are produced like quote unquote faster. Okay, yeah, so this is how much that coordinate changes for a change in t, how much that coordinate changes for a change in t. So what do you notice about both of the derivatives with respect to y? See that they're negative, and so what does that mean? What does that mean in this situation?
Y value is decreasing.
Yeah, so for an increase in t, y is going to go down. That's what we're seeing. Y is decreasing, but x does what? Increases, and that's why it has a positive rate of change. Okay, so let's talk about circles. Any questions on what we've done so far? Or let's go back to that. I said we're going to do this ellipse here. So 6. Let's look at this. Okay, so this is parametric equations. X equals 2 sine 6 pi t, and y equals cosine 6 pi t. So the key here is we have the same argument of sine and cosine. I'm able to change the argument here. When I change the argument, that's when kind of bets are off. We want to focus now on when the argument is the same. We got 6 pi t here and 6 pi t here. Okay, and what do you know? So we get an ellipse. So can we write the equation of the ellipse? In x and y. So is y a function of x? Is y a function of x? You should be thinking no, right? You should be thinking no. So it doesn't make sense to like solve t in terms of x. You get inverse sine, which is, we know that there's issues with that in terms of domain issues. So because y can't be written as a function of x, that's an indication that we don't want to solve for t and plug it into this one. Cosine 6 pi of something sine inverse. Okay, this is not the way to go. So we want something else to eliminate t and write this thing as an equation dealing with x and y. So what could we do? Any ideas of algebraic things that you've learned that might be able to eliminate t and to leave us just an equation of x and y? Who knows their trig, right? So this is about having some, so I think Martin has an idea. Anybody else? Jonathan?
Is it possible to use the sine squared of x plus cosine squared of x equals 1?
Is that what you were going to say, Martin?
I was thinking like dividing sine and cosine to get jump.
But then we still have t. We'd have tangent of t. The goal is to get rid of t. So you want, okay?
So we could use that in which we can't
So he's suggesting we do sine squared of theta, or whatever, plus cosine squared of theta equals 1. Using this, the Pythagorean identity. Can we use that to eliminate t?
like, can we replace the sine and cosine with the x and y by trying to like
Yeah, you got the right idea. So if we want to get just sine and square it, what would that be? Just sine by itself squared in this case would be what?
X squared.
Would it be x squared? We got this 2 to take care of, right? We just want sine squared.
Can we move the 2?
What's that?
Divide the x by 2.
Yeah, so we could do, say, x over 2 is our sine, right? 6 by t. And
Our y is just y.
y is cosine of 6 by t.
But since it's squared in that equation, we gotta square those two.
Right, so we're going to square sine, and if we squared sine and we squared cosine squared cosine and added them together, we would get what? 1. So then, does that eliminate t? Do you see how that eliminates t? Tina, what would it be? Uh-huh.
You subtract, oh, minus
We're setting this up right here. We're setting this up, right? So plus
y squared.
equals?
1.
Do you see it? See what happened? So if sine is x over 2, then sine squared is x over 2 quantity squared. And then cosine is y, so then that's y squared. And then sine squared plus cosine squared equals 1. Bye bye t. It's all gone. See that? And then remember what our, so this is the equation of ellipse. What is our standard equation of ellipse? Remember what it was? An ellipse is? X squared over a squared plus y squared over b squared equals 1. Now that's centered at 0, 0. Okay? Let's center 0, 0. So then what was A? A is the from here to here. That's the value of A. Does it match? What's our value of A here? If it's x squared over a squared, then A is 2, and that's what we see, right? So this is 2 right here. And then what is B in this ellipse? 1, and that's what we see. Yeah, right there. So A equals 2, B equals 1. So example. (16x squared plus y squared over 9 equals 1). Write that curve parametrically. X equals a function of t, and y equals some other function of t. That would generate that ellipse. See if you can do it. Keep passing out. Stuff. Okay, so we get x over 1/4 squared plus y over 3 squared. Okay, if it's going to be ellipse, it's got to be this form. So we need x squared over something squared. That's going to be over 1/16 squared, right? over 1/16, which is 1/4 squared.
The other side.
So x over 1/4 equals, no, so this is, if this squared plus this squared equals 1, then that thing is, no, not 1 minus. Now we've got it in the form of cosine squared plus sine squared equals 1, or sine squared plus cosine squared equals 1. You see? So this equals sine of t. And this equals cosine of t. Therefore, x equals 1/4 sine t, y equals 3 cosine t.
Could you just?
Go ahead.
I was working towards the same answer, but I made my x 4x instead of putting it over. And I said that a was 1. Does that work, or does it have to be x by itself?
You gotta have, for a ellipse centered at the origin, it has to look like this. And that's the form that we can then apply this. Sine squared plus cosine squared equals 1. So could I have said, any questions on that? Could I have said x over 1/4 equals cosine t? And y over 3 equals sine t? Would that have made this true? Would that still be that squared plus that squared equals 1?
Yeah.
And what would be, so, same function? So here's possibility number 1, possibility number 2. Same function or different function? Different function. What's the same? The curve that it produces, right? The locus of points is the same, but the way that it produces that locus of points is different. Different values of t will give a different point on the curve in each case. So let's see it. So questions before I erase the screen? Yeah, please.
How did you get 1/4? 1/4.
Because this is x squared over 1/16, right?
That's 16.
Right? But we need it over something squared. So I'm going to start by doing x squared over 1/16.
Oh, okay.
And I need it over something squared. That's 1/4 squared.
Okay.
Do you see it?
Yeah.
Okay. Other questions before I erase? Okay, so let's do this. So what do we say? Equals 1/4. What do we have first? Sine t? And then 3 cosine t. But then we wanted to say, and we'll do that, say in black. And then in red, we said we want to do, oops, 1/4 cosine t. And 3. Okay, so do I get the same curve in both cases? So I've got to show this. I want to show the whole thing. What should I set my parameter t? Let's do this for t greater than n. See if that works. So if I want to see the whole curve, what am I going to set t? Anybody? Why do I not see the whole curve? I only see the sliver of it. Really? What does t represent here? So what does our parameter in this case represent? Angle, right? Angle measure. Angle measure is the input into sine and cosine. So if I want to show the full ellipse, what do I have to specify to show the whole thing? Right now I'm showing t from 0 to 1.
1080.
Yeah, I need an angle measure that's going to show me the whole rotation, right? Which is pi. There it is, okay? And so we've got B is 3, and A is the 1/4. Sorry. I don't know how to do that. Okay, anyway. So this is showing the whole thing. And so now if I turn this one off and turn this one on, in red, shows the same exact curve. But how is it different? If t equals 0, which point do I get here? T equals 0 gives me
0, 3.
0, 3. And if t equals 0 on this one, the red one?
1/4 to 0.
1/4, 0. So when t equals 0 on the red one, I get this point. This is the way we like to think of it, right? X being the x coordinate, cosine, and y being the sine coordinate. So this is going to be our counterclockwise loop starting at this right side. This one is going to start at up here when t equals 0. It's going to be 0, 3. And so let's say, so we know the direction of this, right? Cosine and sine, the direction is going to be counterclockwise. What will the direction be for this one? Figure it out. Will it be counterclockwise or clockwise? How can you figure it out? So we know when t equals 0, we get 0, 3. So will it generate points this way, or will it generate points this way? How can you figure it out?
Put in a really small value of t and see which way it goes.
Well, yeah, okay, make it easier on yourself, right? Yeah, sure. What do you want to do? Make it easy on yourself with things that you know what you could calculate this easy, right?
Like pi over 6.
If you could do pi over 6, or you could even just do pi over 2, right? So at pi over 2, what point do we get?
1/4 to 0.
You said 1/4, 0. Agree? So which way?
Clockwise.
This one gives it clockwise, right? So if we do 1/4 sine, 3 cosine, so let me turn the black one on. So I'll turn off the red one, turn on the black one, which is what changes the color, but because we know it's the same curve. But this is going to generate the points clockwise. It's going to start it at this top point and it's going to generate clockwise, versus we know the red one from our past experience, when x is cosine and y is sine, which is how they're defined, it's going to generate counterclockwise from that right side of the loop. Okay, so we got to do something a little harder here. Will it work? There we go. So we have this parametric curve. X equals 1 plus 9 cosine t, y equals 4 plus 9 sine t. And we want to write it in this form. X minus h squared plus y minus k squared equals r squared. So what does that have written all over it, that form right there? Okay, yeah, so that's the equation of circle, center, what? It's a circle with center, what? HK. And a radius of? R. Okay? So how are we going to do this? So we've got these parametric equations, and we got to get them into the form something squared plus something squared equals r squared. How are we going to do it? What are we going to use? Do you see any t's in there? There's no t's. We got to get t out of here. How can we get t out of this thing? Or eliminate t?
Cosine and sine by itself.
Okay, go. Do it. Work on it. So what's the key? Cosine squared t plus sine squared t equals 1. So what do we need? We need to get what cosine equals. And we need to get what sine equals, and we need to apply this. We can get what cosine equals and what sine equals, we can substitute into this, and then say it equals 1, and then t's are gone. So what does cosine equal? What does cosine equal? X minus 1 over 9. There's cosine squared, right? And what does sine equal? 1 minus 4 over 9. And so therefore that I did cosine squared plus sine squared, and it equals 1. T is gone. But now it needs to get to look like this, right? So how do we get it to look like this?
Try to get the 9s out.
Yeah, so this is just, what is 9? We can just do that, sorry, 9 squared. Okay, and then we're one step away, right? What do we got? Yeah, so then we got x minus 1 squared plus y minus 4 squared equals, what's the center of, so this is going to form what kind of curve? So this, as parametric function, is equivalent to this equation of x and y. Those are equivalent. So what kind of curve is this going to generate? Yeah, so this is, right, we said this is the equation of a circle. What's the center? 1/4. Radius?
9.
9. So these parametric equations, so what is a circle? Circle is just a special case of an ellipse, right? Where your directrix are the same. Your distance A and your B are the same. Okay? So this is just going to be a circle with center 1/4 and radius 9. Here are the parametric equations for that. So this is the way you did it when you did conic sections and pre-algebra. Now there's another way to write that. X is a function of t and y is a function of t. Now they're restricting t. They're saying start t at pi over 2 and end t at 3 pi over 2. So that's just going to give you part of that circle. So it's going to give you half of the circle. Some half. How do you figure out which half? Well, plug in your value t and get the point xy. Plug in your final value t, get the point xy. So you can determine the starting and ending point and the direction of that curve. This problem make sense? Okay, so now let's look at this kind of cool example that I showed you earlier. Any questions about circles? So circles and ellipses, going back and forth between the ellipse form and the parametric form or the circle form is all a matter of the centerpiece kind of that algebraic work is this, that cosine squared plus sine squared equals 1. Okay, that's your kind of your anchor that allows you to go back and forth between the equation, the x and y equation form of your circle or your ellipse, and your parametric form. Anybody have a question? All right, so let's look back at this example that I showed you, this kind of cool looking curve. And say we're interested in where the tangent line is either horizontal or vertical. So where in this curve do you see the tangent line as horizontal? How many places? Where do you see that? So, oh, and by the way, I have two different ways of writing this function. So this red, let's see, red and blue. So anyway, I've written the function in two different ways, and I've shown that by the red point and the blue point. Let me do this in gray. You still see it? Let's do black. How about blue? That's good. All right. So one of the ways I've written it is in red, and the other way I've written it is in blue. So two different ways of writing the same curve. So what about dx and dy t right now? Versus now. Let's just think about dy dt, okay? Let's do it again. So what about dy dt as it comes through here? What about dy dt? What could you say? Dy dt. All right, so what about dy dt?
Yeah, change from negative to positive. Back to negative.
Okay, well, there's a little bit. A lot going on there. Okay, so just watch. Okay, so let's just look at this part right in here. What about dy dt? What are some things you can say about dy dt for the t values that generate these points through here? What could you say?
It's negative.
He wants negative. Agree with that? For increase in t, you're getting a decrease in y. What else could you say?
Concave down.
No, about dy dt, the value of dy dt. So for instance, through there compared to through here, what would you say about the value, the negative value of dy dt for through this part here? I can't control it. hard. So this part here versus this part here.
It's less negative.
Right. So through here, you see for a change in t, you're getting not much of a change in y. Or the dots move slow, right? The dots move slow, so you're getting less of a change in y for the same change in t. But then when you get here for a change in t, what do you see about the change in y? It's a lot. So here you'd have kind of low negative values through this part, and then when you got to here, you're going to have high negative values. For a change in t, you get a large change in y. So where is a tangent line to this horizontal? Do you see any places where the tangent line is horizontal? Let me turn one of those off. Turn the red one off. So where along here for what? Where do you see the tangent line horizontal?
Very top curve.
It's at the very top. Anywhere else?
Also, when it goes back.
Okay, there's two places. All right, so maybe I'll just use my technology just to estimate. This slider gives me the t value. Actually, hold on. I want to turn this one on. This one off. Okay, that's what I want. So let's estimate for what value of t, something like around here, right? So it looks like I got -1, -0.9, something like that, around -1, okay? For t equals -1, so we're thinking maybe there's a horizontal, and then where else? T equals maybe 0.8 or something like this, positive 0.8. Okay, so how can we find it exactly? We want to find the exact values of t and then easily the coordinates for these where there's a horizontal tangent. What are we going to do? How do we do that? Okay, the derivative. We're on a horizontal tangent. So for a change in t, what do we want? For a change in t, what? 0. But what 0? We got two equations now. And we got x and we got y, and we could do dx dt and we could do dy dt. Both 0. So for a change in t, both derivatives are 0. So at this place right here, do both x and y pause for a change in t at this high point? What pauses? X or y or both? Just y, right? So only y stops for a change in t. X has a positive value there. So what are we going to do? We're going to take dy dt. We want dy dt to be, for a change in t, we don't want a change in y. That's horizontal movement, right? For a change in t, no change in y. So dy dt equals 0, right? So what does dy dt equals 0 will give us? So dy dt is -8 t cubed plus 6t squared. 6t, thank you, sorry. Then what? -1. Okay, and so then we would need to do what? Find values of t that make that 0. that make this true, that dy dt is 0. So this one isn't immediately apparent. If this was a quadratic, what could you do? So if you got a quadratic, how would you find values of t that make it 0? That's just pre-calculus. Factor, use the quadratic formula, right? We have a cubic. So I suspect, I could be wrong, but that this let's see. Okay, it's not 1. So let's use a graphical method to do this. I'm just going to graph this, and we're just going to look for where it's 0. So I'm just going to say y equals negative 8x cubed plus 6x minus 1. What did I do wrong? Something's wrong. What did we do wrong? Negative 8t cubed plus 6t minus 1.
I think, because doesn't the original graph have that third spot where it's got a...
But there should be a 0. There should be a 0 right under here.
Oh.
What are we doing wrong here?
Maybe it's way up there. Since those two are both maximum, maybe it's like farther up.
Oh, well, we're finding t values equal to 0, so they shouldn't match up with the x value.
Oh, right. Right. Thank you. Right. Because this is now, for the purple graph, this is t. Right. Okay, good. So we thought something close to negative 1. So that's right here. So that right there is telling us that when this value is negative 9.36, this thing is 0. So negative 0.94. Okay, and then we expected another one around 0.8, and that's right there. Oh, there's somewhere else.
Isn't that where the graph comes down?
Yeah. Did you notice that before? Yeah. Okay, good for you. I didn't see it. Okay, so then this one is this root. So I graph this, and I want to find the roots of this equation. The roots of this equation will be where it's 0, and that's what we said dy dt. So we want dy dt to be 0. So t equals, this one here is 0.766. But there's another one. T equals 0.173. And does everyone see where on the original curve this one is? So where else is there a horizontal tangent here? T equals 0.174. Yeah, there's like, it kind of, we'll have to zoom in there to see it. Right around there. So there's another one where this dips down around here like this. Right there. So how would we get the coordinates? So now we've got these 3 t values that give us a horizontal tangent. How would we get the x and y coordinates of those points? That should be easy. How would we get the x and y coordinates of those points? Yeah, so you're gonna plug your t in. You're gonna plug t in, and it will just generate the corresponding. We're doing this, right? So to find a vertical tangent, then for a change in t, we want no change in x. So we're gonna set what? dx dt to 0, and dx dt is. This is very attainable here. So what? How do we solve that for 0? You factor out 3t, we get. Okay, so for what values of t do we get a vertical tangent? Okay, so let's, and then what are the coordinates? So when t equals 0, we get
1, 4.
1, 4. Good. And then when t equals 2, we get?
-3, -18.
Everyone able to do that?
Yep.
Cool. All right, so let's see it in action here. So t equals 2. Boom, right there. Right there, if I zoom in, it's going vertical just for a moment right there at, this is t equals 2, and then our x-coordinate is -3, and our y-coordinate is -18. Pretty cool? And then the other place. Need to zoom in on that to see it. Oh wait, yeah, that's right. So if I zoom in, right there on the nose, t equals 0, x equals 1, y equals 4. Vertical tangent. Okay, so then Jonathan was talking about, before was talking about dy dx. So can we find, say right, let's say at this point here, and this point here. So first let's see, are we able to do that? No, too hard. Too hard. Okay, so say for, let's just pick a point. T equals -1/2. So at t equals -1/2, what would you estimate dy dx to be? So here's t equals -1/2. Could you just, before we calculate it, can you estimate what you think the value of dy dx would be? So now this is saying for a change in x, for a small change in x, how much does y change proportionally to that change in x? That's what we're saying. So what would you, just as a guess before we calculate it, what would you think? Salvador, could you guess?
Use the derivative of.
No, I want you to guess based on what you see. So I've got an even scale here, right? I've got an even scale, 1-to-1 scale in the graph. So could you make a guess at what dy dx would be at this moment for a change in x? Zoom in. -2, I heard. -1, I heard. So for a change in x, we're saying how much does y change proportionally to that change in x? More negative or less negative than -1? A little, it looks to me just a little bit less negative than 1. That for a change in x, you're going to go a little bit less than that. So what would we guess? Negative 3/4 or negative 0.8 or something like that. So let's try that. Now let's actually find it. How are we going to find dy dx from this without finding? We don't have y as a function of x. And we said it would be awful to try to figure it out because these are high degree polynomials. So instead, how can we get dy dx? Well, we can get it from the derivatives that we can get. We can get dy dt and we can get dx dt. What should we do? How are we going to get dy dx out of those?
dy dt over
Yeah, exactly. So take dy dt. It's just kind of intuitive, right? All right, so we're going to take dy dt over dx dt. And dy dt is, that was our negative 8t cubed plus 6t minus 1, is that right? Over 3t squared minus 6t. Cool, and so what do we want? We wanted that at t equals negative 1/2. So that's a piece of cake, right? We're just plug it in. Negative 8, I'll say a cubed plus 6a minus 1, all divided by 3a squared minus 6a, and I want my a value to be what? And we thought it was going to be a little bit less negative than negative 1, negative 0.8. See what happened? There it is, right there. Okay. What about the second derivative? So oh, sorry. Does it help? No one else needed that. So sorry, I didn't mean to do that. So our first derivative is this. Okay. Our second derivative would be what? So now the second derivative is taking basically our y again with respect to x. We're taking the derivative of the derivative with respect to x. So that means wherever we have y, we're going to have the derivative with respect to x. So what will that look like? The derivative of dy dx with respect to t over dx dt. So the second derivative is taking the derivative of the derivative with respect to x, right? We're taking the derivative of this with respect to x. Well, we had that before, right? So we know what the derivative of something is with respect to x. It's that derivative of that with respect to t over dx dt. So then I can just take the derivative of the derivative with respect to x with respect to t over dx dt. You see it? Notice that it's not, the second derivative is not this second derivative divided by this second derivative. Because we're taking a second derivative with respect to x. So this is what we want, and so where there's a y, we're going to do the derivative of dy dx with respect to t. So what does that mean? That means we're going to take the derivative of this right here. Just imagine that has t's in it, because that's our dy dx, right? And what are we going to do? We're going to differentiate that with respect to t. We're going to take the derivative of that with respect to t. And so that would be, how would we do that? Quotient rule. We won't do it. I'll just talk through it, okay? So that will be quotient rule for this particular example. And for most, right? Because you're going to have a quotient of t's. So this will be quotient rule, and then again over dx dt, which we already have, which is 3a squared minus 6a, or 3t squared minus 6t. So this will be quotient rule divided by the same thing we had for dx dt before. So in this example, it would be 3t squared minus 6t. Did you follow that? Is that okay? All right. So the last thing is area under the curve. Okay, so area under a parametric curve. Let's talk about that. And let's look at the same example. So area. So we know that area is the integral from a to b of y as a function of x dx. Or, in other words, y dx. So if we had some function and we wanted to get the area from a to b, or the difference of areas from a to b with the x-axis of the function f of x, we know that's integral, right? We know that's integral. So that's the same thing as just writing a to b of y dx, but now, so in parametric form, what is y? Y is what? Is some function of t, right? So we got x equals f of t, and y equals g of t. So y equals g of t, and then what would dx be? So if x is f of t, then dx would be? F prime of t, chain rule, dt. And then, so this is going to be then from t equals some starting value of t to some ending value of t. So let's say we wanted to find, for this one, we want to find the area from, let's say, I didn't want to do that. Just remove it. -1, where's -1? So what if we took the integral from -1 to 0 of this thing? What area would we get? So -1 is about here. And 0 was, where was it? On the side or on the bottom? So if we integrated from t equals -1 to t equals 0, what area would we get? What area would we get? Can you see it? So we're going to start there at t equals 1 to t equals 0. So if you just imagine that much of the curve, then you might be able to see it a little better. So if we integrate, and so it's going to be the same thing, right? Because it came from this. It came from y dx. That we set up the integral for the area parametrically. So what area will we get from t equals -1 to t equals 0? What we get, so it's going to be the same as before. Since it came from the same thing as before, it's going to be the area below the curve to the x-axis. Okay. Okay, and then if we did so then what if we did the integral? If we went from 0 to 1.45. So this is t equals 1.45. Is that there at that x-intercept? Now I'm going to integrate from t equals 0 to 1.45. And what area will I get there? This is going to have somewhat of a cool ending. Cool to me. I'm trying to get to this kind of cool conclusion. So there's the curve from 0 where it's vertical to there. So if I integrate from 0 to 4.45, I'm going backwards this way. I'm going to get what? The opposite of this area. Because I'm going backwards in x, it's going to give me a negative value, right? It's going to give me that red area, but because I'm going backwards in x from 0 to 1.45, it's going to be negative. So then what if I did an integral from -1 to 1.45? What will we get? Yeah, so if I do the integral from -1 to 1.45, do you see what it's going to give? So it's going to integrate from 1 to 0, and it's going to give me all the blue. And then it's going to keep going from 0 to 1.45, and it's going to subtract out all the red. So you're going to get the area in the curve. You're going to get this. That's really cool. You're going to get the area inside the curve here, starting at -1. You're going to get this black region. You don't have to. It does it for you, right? It will give you that. Truly give you that area inside there. Okay, and so then just finding these areas is just a matter of setting up this integral, getting your t's right, and doing the integration. So that's just old hat. You're going to apply integration techniques that we've learned. Okay. Okay, web work for tomorrow. got one more thing to do fast. Big thing. Lindsay. Kevin.
It's not